morning and welcome back. You just heard that we have an opening theme. I would like to take this opportunity to express my gratitude to my daughter, Miss Zhang Peiqi. She composed the music for us. Thank her. And today we will talk about other materials such as conducting sphere. So actually we will start from page 11. Let's move to page 11. Page 11, we will talk about scattering by a small, perfectly conducting sphere. Okay, I will show you the induced uh, electric dipole and magnetic dipole. Okay, then I will show you how to derive the dipole moment, especially the magnetic dipole moment. Then we will talk about perturbation theory of scattering. Due to a very small scatterer, that's the molecule, that's the air, okay? And I will skip this part and jump to here. I'll try to explain why the sky is blue and it's red at sunset, okay? From perturbation, from scattering, okay? We will use 4 pages to explain what happened here. Okay, before we start, I would like to go back to page 1 because page 1 is extremely important for scattering. Go back to page 1. Okay, page 1 tells us if we have incident wave, the incident wave is a plane wave. So we can write into E incident, E epsilon 0, E0 exponential IKN0 dot x. Okay, epsilon 0 means the polarization. It can be in x direction, y direction, or z direction. It can be real quantity, a real vector, or a complex vector to express the circularly polarized wave. Okay, so we use the notation, just like the notation we use in chapter 6 and 7. E0 is the amplitude of the wave, and K is the wave number. N0 just expresses the direction of propagation, just like the Poynting vector's directions. X is the observer's directions. So X is the observer. In chapter 9, we calculate vector potential and then derive the H field. From H field, we can calculate E field. But here, just like this one, we calculate vector potential first and calculate H field. From H field, we calculate E field. We calculate magnetic dipole moment and then H field, and H field, E field. The same process. But now, normally we prefer to express electric field because our scattering materials are commonly electric field. So most of the people prefer to express electric field. Okay, actually no difference. You can express H field first and derive E field, or express E field and calculate H field. The incident wave from this direction, okay? So there's the Poynting vector. E field could be in X direction, Y direction. It's simple. So H field can be calculated from here, from these properties. and it will induce electric dipole and magnetic dipole. High order terms, quadruple terms, are not very important because we consider a long wavelength limit, and it will generate wave propagate in the direction of n. That's the observer's position. So electric field is called SC, HSC. Okay, so we consider here, starting from here, and then we can rewrite these equations. So ESC come from electric dipole and magnetic dipole. Okay, last time I show you how to derive this equation from these simple properties and use their vector triple products. We already show you. If you don't remember, please check the lecture notes, previous episodes. Okay, so that's very important. We consider a long wavelength limit. That is, the physical dimension of the material is much smaller than the wavelength of the incident wave. Okay, so we define a figure of Mary. That is the scattered power relative to the incident power. But incident power is easy to calculate, but scattered power, it will scatter to all the directions. So it's not easy to calculate. Therefore, instead of scattered power, we define a differential cross sections, differential scattering cross section. That is, it depends on polarization, not just power, but polarization, and depends on direction of propagation. For example, the incident wave is in this direction, for example, z direction, and polarization is in these directions. And incident wave is a scattered wave is in this direction, and polarization is in these directions. And this is a differential scattering cross sections. It's not easy to understand. So I will explain this idea again. So for a circularly polarized state, epsilon can be written as this form. And we have two polarization, epsilon 1, epsilon 2. You might imagine the epsilon 1, this is the n0 in the z direction. So epsilon 1 in x direction, epsilon 2 in y directions, and vice versa. Not exactly correct. They are perpendicular to each other, just like this one, but not necessarily be in x direction or y direction. So second, epsilon 0, and this one is perpendicular. Why? Because it's in outside the source, long wavelength limit. So it's a plane wave. Plane wave polarization and the direction of propagation is perpendicular. Okay? And once again, epsilon complex conjugate perpendicular to n because scattering wave is in this direction, and so they should be perpendicular to each other. And this one is normalized, and this one is also normalized. Epsilon is not necessarily the direction of E scattering, not necessarily. Okay? You can define your direction. Up to you. Epsilon star complex conjugate dot E scattering gives the E component of ESC. So next slide, I will show you how to calculate this one. Okay, we rewrite this one, just write it down. and substitute everything. That's the incident wave, that's the scattered wave, and how to calculate this one. Eventually, we got a very simple equations. And differential scattering cross-section is proportional to k to the fourth, k to the fourth power, and is inverse proportional to intensity square. And actually, intensity were proportional to P, proportional to M. So intensity can be cancelled. Okay? And that's the direction of epsilon to be determined. Direction of an epsilon in x direction or y direction, up to you. We will define very soon. So we can simplify equation 10.3 to equation 10.4 by substituting incident wave and scattered wave due to electric dipole and magnetic dipole. Electric dipole and magnetic dipole are to be determined. Okay? So first, we will consider dielectric sphere. We like dielectric sphere because no magnetic response, just electric dipole only. And electric dipole we can use the knowledge we learned in chapter 4. In chapter 4, we obtained the electric dipole moment P induced on the scatterer by E incident. So we got these relations. So now just substitute this P to the equation 10.4 and M 0. That's why we start from this special case. Okay, that's very convenient. So eventually k to the fourth and epsilon r minus 1, epsilon r plus 2, absolute value square. And this is the incident wave polarization and scattered polarization square. Okay, so when epsilon r equals 1, let's vacuum, nothing. So this is 0, no differential curve, no scattering, differential scattering cross section. So in this case, epsilon r equals 0, equals 1. Nothing changed, no scattered wave. Okay. This is the reminder how to calculate dielectric electric dipole. We use the separational variable and compare the equations. And eventually, we got this property. The P is proportional to the size, the volume of dielectric sphere, and intensity. So P is proportional to E0, and the direction is exactly the same as well as this one. So epsilon is very, very large if then this one will be close to 1. So largest value of P is 4 pi epsilon 0 a cubed E0. Okay, that's the volume times epsilon 0 E0, proportional to the volume. Okay, so let's define the scattering plane. Since this part are quite important, so please allow me to reiterate to start to show you the definition again. We define the N0. N0 is the direction of the incident wave N is the direction of scattered wave. Okay, incident wave here, scattered wave here, and this span a plane called. Normally, we prefer the incident wave, the direction of the incident wave in a z direction, and scattered wave. Scattered wave we can align line on xz plane, xz plane. So that's the scattered wave here. The orientation theta phi of unit vector epsilon 0. Epsilon 0 can be in x, y plane, just line on x, y plane. Okay, it can be linearly polarized or circularly polarized. Depends on what you want. So it's in pi over 2 theta equals pi over 2. Okay, xy plane. And in direction, the angle phi 0. Phi 0 is the polarization of the incident wave. Phi 0 later on can be 0 to 2 pi. Okay, we still need another coordinate, epsilon 1. This is the direction of scattered wave. And we can define epsilon 2 easily because we know this one is perpendicular to this one. This n is lying on SZ plane and y will be perpendicular to XZ plane. So we can define epsilon 2 along the y-axis. So x theta equals pi over 2 and phi equals pi over 2. Okay, this one is easy. And we need another direction that is perpendicular to n and epsilon 2. How? We can define another coordinate. This is theta. So we just define another coordinate, 2 pi over, the angle is still on the xz plane, but the angle is 2 pi plus theta. This is theta. This is 2 pi plus theta. So obviously the angle between n and epsilon 1 will be pi over 2. Okay, by doing so, that's the polarization of the incident wave. That's the polarization state of the scattered wave parallel to the scattering plane. Polarization here, parallel to the scattering plane. Okay, obviously that will be perpendicular to the scattering plane. Okay, so we define something parallel to the scattering plane, perpendicular to the scattering plane. That's important. The most difficult part of chapter 10 is you need to imagine the three-dimensional relationship. That's normally quite difficult for most of the students. Okay, by doing so, substitute everything, we can derive parallel the cross-section, scattering, differential scattering cross-section, parallel, differential scattering cross-section, perpendicular. We can determine different polarization. Okay, different polarization state, much easier to understand. Okay, just substitute everything. And we can define a linear polarized, the degree of polarization of the scattered radiation, degree of polarization of the scattered diffractions. Okay, and we allow phi 0, that is the incident wave can be changed from 0 to 2 pi. So it's incident angle average. That means the incident wave is random, not polarized in one direction, unlike laser, unlike wave, microwave. Because for visible light, like the sunlight, phi zero should be N is the direction of propagation, but polarization is randomly polarized. Okay, so that gives us a better understanding. Okay, now let's move on. Consider the scattering by a small, perfect, perfectly conducting sphere. Conducting sphere is a conductor, so you might imagine it's not dielectric. So no dielectric, but that's incorrect. The incident wave will induce both dielectric, both electric and magnetic dipole moment. That's very interesting. Why? Because conductors, we have an incident wave. We will polarize. We will change the charge. For example, if the incident wave is polarized in the z direction, then electric field in the z direction. Therefore, we will generate a positive charge. We will induce positive charge in the north pole and negative charge in the south pole. So negative charge in the minus z and positive charge in the plus z. So they will induce an electric dipole. Therefore, they will induce, just like susceptibility is extremely high, just like epsilon r is extremely large, absolute value of epsilon r is extremely large. So the electric dipole will proportional to P. If this is not clear, you can check section 3.3 of our lecture notes, previous semester. And magnetic dipole will be a minus sign. Surprise! It's a minus sign. That means a conducting sphere is an anti-ferromagnetism. It's not proportional. It's inversely proportional to the incident wave. That's very interesting. People always think they should be positive, but it's not. It's not. So it's interesting. I will show you how to calculate M, how to find a relation between M and H in the next problem. Okay, so we have P, we have M. What's next? Substitute everything into equation 10.1 and 10.4. So eventually we got a simple relations. The sigma over the omega k to the fourth, a to the sixth. And that's the polarization. Epsilon 0 minus 1 over 2 n cross epsilon compressed conjugate dot n0 cross n epsilon 0 absolute value square. Okay? P is easy, this one. M is also easy. So we can calculate the differential scattering cross section by consider the contribution from P and M. Okay, so as in example 1, for an unpolarized incident radiation, what does it mean, unpolarized? That's the direction of the incident wave. And polarized means the polarization wave can be here or can be in the x direction or y direction. And here we use unpolarized. Unpolarized means the incident wave can be in the xy plane, randomly distributed. Okay, that is the phi 0 can be 0 or 2 pi, randomly distributed. Okay, so equation 10.14 is by angle average, just like the radiation from the sun is the incident direction is, if you look at the sun, N0 will be from the sun to your eye, so that direction. But the polarization can be in the, if you from the sun to your eye is Z direction, then the polarization will be in the X direction or Y directions and randomly orientated. So that's why we say it's unpolarized. Okay, it depends on what you want. If you study the sunlight, and normally you will consider unpolarized, or you study the radiation from distant star, you use unpolarized. However, if the incident wave is controlled by someone, by a human being, then you should consider polarized incident wave. Okay, depends on your applications. So first, we study sigma parallel cross-section with the polarization parallel to the plane of incident. Plane of incident, the scattering plane, not a plane of incident. Okay, and we got these relations: k to the fourth, a to the sixth over 2 cosine theta minus 1 over 2 f squared d sigma over d omega perpendicular. Take average, angle average, k to the fourth, a to the sixth over 2, 1 minus 1 over 2 cosine theta squared. Okay, so total differential scattering cross section is here. By sum over these two, that's the total. Okay, and pi is defined as, from the definition of pi, we can calculate. And we found an interesting phenomenon. That's the peak occur at theta equals 60 degree. So the average is sigma. That's the integral over all the studied angle will be this one. Again, we found sigma smaller than pi a square. Pi a square because pi a square times k to the fourth, a to the fourth, and Ka is normally very small. So that means if we have a sphere, dielectric sphere, a conducting sphere of 1 millimeter in radius, you might expect the shadow is about pi a square, but its differential scattering cross-section is much smaller than that. This example demonstrates that geometric optics completely break down for lambda. Wave is not propagate in straight directions. We should use Fraunhofer diffractions, not geometric optics. Okay? Fresnel's diffractions. Well, we need physical optics, not geometric optics. Geometric optics, that means just like a laser beam, wave is always in a straight line. and physical optics as in scattering diffraction series. Okay. Next, I will show you how to derive the dipole moment, magnetic dipole moment M, and why M will be a negative sign. That's the solutions. First, let's consider lambda, the wave, the incident wave, is much larger than the physical dimension. We may assume H incident to be uniform. Okay, that's a good assumption. For a perfect conductor, we have E and B inside the sphere, 0. Electric field and magnetic field cannot penetrate for AC components. Okay, for DC, B field can penetrate, but E field cannot. Okay, in section 9.3, we have shown that in a near wrong, that is observer is not too far from, is smaller than lambda. The magnetic dipole radiation has negligible electric fields. Near wrong, we just consider B field, but we don't have to consider E field. So we can assume that close to these regions, we assume that electric field is small. Okay, that's reasonable. So curl of B equals 0, approximately equals 0 outside the sphere. So we can write B equals gradient phi. You might wondering why not add a minus sign, because phi here is not very important. It's unlike a potential. It's just a notations. So we don't need to add a minus sign here. We also know divergence B is always 0. So by substituting Laplacian gradient phi into here, we got Laplacian phi equals 0. So the solution is simple here. In terms of spherical coordinates, R is from here, origin, to here, and P is associated Legendre polynomial. Q is another solutions. And for the angle dependence, exponential Im phi plus exponential minus Im phi. That's the linear combination of these two times the linear combination of these two times the linear combination of these two. This model is valid for r smaller than lambda, which is sufficient for us to find the dipole moment for a sphere with radius smaller than lambda. Okay, so what's next? We have the general solutions. Next one, use the boundary conditions to determine the coefficients. First, we consider magnetic field outside, and very far away, we still have H field. Why? Because the incident field is given. So very far away, H0, H incident, EZ. Okay, so we got this one. Mu0 H inc over Z. So text the gradient, we got mu0 H inc. And B and H has a simple relations, H mu0. So This one, people normally will forget about this one, but you should keep this in mind. If we have a uniform H field, we have uniform E field, we still have to consider this one, the same argument we learned before. And Z is here, so it's R cosine theta. Okay, that's the first one, first boundary conditions. Second, when B perpendicular to A, normal component of B field should be 0. How to calculate the normal component of B field? Here, we use partial R, normal component, that's R directions. R direction of B field, just use these properties. It's 0. Okay, what else? Phi is independent of phi. Why? As mutual symmetry. Okay, so we can assume no phi dependence. Good. M equals 0. Good news. We can eliminate this part. Okay, and phi is finite at cosine theta equals 1 and minus 1. So equals theta equals 0. It should be finite. Theta equals pi. It should be finite as well. By doing so, we can eliminate Q. Okay, that's good news. So all we have is this one. But remember, we can use very, very far away to determine this one. Okay, so we know A1 equals mu 0 H incident, and other L, AL equals 0. Nothing, just one turns. And C1, C0, C high order term is not determined. So we just write it down, just R, L, one term, R minus L minus 1 to be determined. How to determine? Remember, we still have another boundary conditions. Take the R derivative. We got this one from here. We got this one. And other terms. So it's clear. CL equals 0 for L equals 0, 1, 2, 3, 2, 3. And only one term survives, C1. So C1 equals 1 over 2 mu 0 A to the C1 equals this one. This one equals this one. So C1 is proportional to 1 over 2 mu 0 A to the A cubed HINC. Okay, others are 0. So eventually we got two terms. R equals 1 and minus 1. R equals 1 terms. So from B, due to the sphere, conducting sphere, we just consider gradient phi. We have only two terms, 1, 2. Okay, and this one will give us the first term will give us the incident wave, but the second term will be the incident wave induced magnetic dipole, and dipole will radiate the B field. So dipole radiation, electric magnetic dipole radiation is shown here. Minus mu 0 8 cubed over 2 HINC here. Comparing with 5.41, we found that the magnetic dipole field produced by a dipole moment produce that is magnetic dipole field. Magnetic dipole produce here. Okay, you can compare with this one. it can be considered as extra bonus. And I will stop here. Yeah. Next time we will talk about perturbation theory of scattering. We have pretty good progress, so we don't have to be hurry. And you have to next Tuesday you will have we will have our first midterm exam. It's open book, and good luck. Okay, see you next time. Bye bye.